I ended the last class by introducing the Sweedler notation for computing in coalgebras. Yeah. And actually, I was looking over the video and I realized that I made a small but important typo. That in the notes I didn't make the mistake, but on the board I just copied it wrong. So let me just start by reviewing that and correcting this. So. So remember that the idea is that if I have a function from a product of C, so C is a coalgebra, right? And I have a function from a product of C's to somewhere. Let's call it V. And this is multilinear. So we know that any multilinear function from this to V descends to a function from the tensor product then the Sweedler notation for this is that if we take f bar and we apply it to, so let's say there's n things here. So if we take the n minus first coproduct, so we take the coproduct n minus 1 times, we're going to get something in the nth tensor product. And our notation for this is going to be, I mean, remember that if I don't have the f bar, then this looks like this, right? C1 tensor up to Cn. That's the Sweedler notation for the n minus first coproduct. And now if we put this function in front, then what we do is that we just put that function here. And I wrote it like this, but it's customary to just do it like this instead. Okay, which is not terribly important, but anyway, so that's that. And so what I wanted to do is do some practice. Okay, so you'll see in your homework that there's really a bunch of exercises on practicing with this notation, but I want to do at least one complete example. Okay, so let's do an example of an identity proved in Sweedler notation. So let's say that we want to prove the following identity. Prove that this is true. Okay? So that's an identity in Sweedler notation, and we have to understand what this identity means and and how do we prove it, okay? And so how can we think about this? Well, so the first thing is that this right-hand side is easy, right? The right-hand side is just the coproduct evaluated at C. And this is something, okay? And it's a function of taking the double coproduct, right? So what is this thing? Well, basically I have the following thing. I mean, let's see what's a good way to say this. Where do we see the third coproduct, I mean, the third tensor product naturally in a coalgebra? Well, remember that the coalgebra has the diagram from C to C tensor C to C tensor C tensor C. And since this lives in the third tensor product, maybe that's where we should be looking for this. Okay? So we have our we have our commutative diagram here. This is delta, delta, delta tensor the identity, and identity tensor delta. Okay? And now let's look for this thing. Okay? So what does this mean? Now let me kind of try to brainstorm a little bit and to see what we can do here. So if we start with C, and then we apply delta, and then this again, then this is going to give me. I mean, let me show you this kind of informal way of using the notation, where if you take an element C here, then here is going to go to the coproduct, which we write in the sum notation, but actually let's just write it like this. Okay. So this goes to this, and then there's the summation in front. Now, when I send it to here, what do I get? Well, it's going to be in lazy Sweedler notation is going to look like this. Right? But that's not what I have. I have this. Okay? So what can I do to get from here to this thing? I want to apply identity tensor epsilon tensor identity. And that's going to be a map from C, C, C to C, C, C. And so I need to put that somewhere, so just put it here maybe. And here I'm applying the map identity tensor epsilon tensor identity. Okay? And then somehow I take this guy, and then this guy lives over here, right? So C1 okay.
Isn't it C tensor K tensor C?
Oh yeah, thank you. Thank you. So epsilon is the co-unit which sends C to the ground field. That's right. So this is just a constant in the field, right? And so it seems that the left-hand side is what happens when I take this path around here. Okay? Now, what is the right-hand side? Well, here we're going from here to here, and again here, the place this would go is this one. Okay? And so somehow it seems that what this identity is saying is that if I take this map in this direction, I get the same thing as if I take this one. Okay? So how can I justify that what I get here is the same as what I get over there? Well, probably by putting a map here relating the two. So can you think of a map that I can put from here to here?
It could be the identity tensor, the isomorphism that connects K tensor C to C.
Uh-huh. So you're suggesting to take the identity tensor, this isomorphism that takes K tensor C to C. In my note, I did it in the other way around. It doesn't really matter, right? So let's just take the F tensor identity, where F is the isomorphism from C tensor K to C. Okay? And so hopefully this all works out. Okay? So we're saying that the left-hand side is to do this. The right-hand side is to do this. Okay. And actually, I'm pushing this through here also. Okay. And so is it true that going around in this direction is the same as going around in this direction? And if so, why? Well, we know that this diagram commutes, right? This part of the diagram commutes, right? Okay. And so this part works out fine. Now what about here? Does this commute? Going this way. I did it backwards again, huh? I made the same mistake that I made last time, because this goes from here to here. And this map goes from here to here. So why does this commute? Well, because if we forget on the rightmost coordinate, this C, and this C, I'm just applying the identity. The identity here, identity here, the identity here. And by the way, this is why I chose F tensor I instead of I tensor F. Because I want the right coordinate to be fixed. Yeah? And what happens to the left side? Well, it goes from C to C tensor C to C tensor K by the maps delta, identity tensor epsilon, and canonical isomorphism. And this is the counitary property. This is the commutation given by the counitary property. Okay? And so if you just write down that this map commutes and that this map commutes, you will have given a proof of this thing. Okay? Any questions about that? Maybe one thing that I will do is just very explicitly think about what this means in Sweedler notation. What is this expression? Sum of C C1 tensor epsilon of C2 tensor C3. Well, so I guess the question that I want to ask myself is, what function are we talking about here that we wrote it like this, right? So this is summation over C of something here. So what is the multilinear function here? The multilinear function that we're talking about is the one that takes f of C d e to this C tensor epsilon d tensor e. Okay. And so what so C tensor. And so when I write Sweedler notation, this is f tilde delta 2 of C. Okay? And so really, what am I doing here? I'm saying I take C, then what is delta 2? Delta 2 is the composition of this map and this map, right? Delta 2 takes you from here to this coproduct. So maybe I'll do this in a different color. This part of the map is precisely the map delta 2. And then from here to here is when I'm applying this like this, okay? And that's how you can see that this symbol for Sweedler notation is really what I was saying that it is, okay? It's really following the arrows around in this way. Now, generally, you're not going to do this in such great care, but I wanted you to see it very explicitly in this case, okay? That's what Sweedler notation means in terms of this picture. Okay. Any questions about that? Okay. And of course, it's crucial to remember that this is an isomorphism. This is the canonical isomorphism. Okay. So we'll do a little bit more practice with Sweedler notation so that we see the advantage of it, because so far it actually seems like kind of a cumbersome notation, but we'll see how it actually becomes useful. Okay. So maybe I'll leave this here so that we remember it, and maybe I'll go over here. And let's talk about a new topic. No les dije que apagaran los teléfonos antes de... Qué pena. Okay, so whenever you define mathematical objects, you want to define the objects and you want to define the morphisms if you can. So what are the morphisms going to be? We already defined coalgebras. Now let's talk about how to map one coalgebra to another one. What does a homomorphism look like? Okay, so let's talk about homomorphisms. And naturally, a homomorphism should be a map from one coalgebra to another coalgebra that respects the linear structure, but also the coalgebra structure. So it should respect the coproduct. Okay. So before I do that, let's do it for algebras. Let me revisit homomorphisms for algebras. So let me make a claim that if you have a linear function from A to B, let me say, I need to say very explicitly, a linear function from A to B is a K-algebra homomorphism if and only if we have some commutative diagrams. Okay. So first we have this one. So what are the maps here? Well, here we have, this is an algebra now, so we have a multiplication map coming from A and a multiplication map coming from B. From A to B we have our function, and from A tensor A to B tensor B we take the tensor product of F and F. So you apply F to each coordinate. Okay? And the other one is this one. So now here the map from K to A is the unit of A, and from K to B is the unit of B. So these need to commute. So this and this commute. Okay? So you can think of this as the definition of algebra homomorphism. And let's verify that this really is what we think it is. Okay, so what is? So what are these properties? So for example, what is this property saying? Let's take a generator here. Okay, so let's say we take A1 tensor A2. Okay, so what happens when I map it in this direction? Maybe I'll write it down. A1 tensor A2. If I map it here, they just get multiplied, right? So I get A1, A2. If I map it this way, I get F of A1 tensor F of A2. Because I apply F to each coordinate. Okay. Now if I go this way, I get A1, A2 goes to F of that. And if I multiply over here, then I get that this goes to F of A1, F of A2. And so saying that this diagram commutes is the same thing as saying that F is a multiplicative function. Okay. So it's kind of a nice pictorial way of writing it. What about this one? Let's take a generator here and take it around this way and around this way. So our generator here is just 1. This is just a field, so you can take the single generator 1. What happens if we take it this way? Well, 1 takes the unit of B to, UB takes 1 to the 1 of B. Now this goes to 1A, and F takes me to F of 1A. And so what I need is that f of 1a should be equal to 1b. Okay? So basically, this means that you respect the multiplication, and this means that you respect the unit. And for a K-algebra homomorphism, we also need to make sure that f is linear, but we started with a condition that f was linear. Okay? So this is one way of thinking about homomorphisms of algebras, and you can imagine that it's useful for us because now we're just going to reverse all the arrows and call that a homomorphism of coalgebras. Okay? So what is a homomorphism for coalgebras? The same thing, but reversed. So linear function from one coalgebra to another one is a K coalgebra homomorphism if and only if these diagrams commute, everything but backwards. So let's see. F goes from C to D. So actually this one doesn't go backwards, right? But now we need to reverse these ones because the tensor, the coproduct goes from here to here and from here to here. Okay? So this is F tensor F. This is the coproduct of C, and this is the coproduct of D. So we're going to ask that commute. And similarly, if I go from C to D, here's F, here's K, and now the co-unit goes in the other direction, right? So the co-unit of C and the co-unit of D. And so these things commute. And so that's going to be my definition of a coalgebra homomorphism. Okay? Now maybe for practice, what is it? How do we write this in Sweedler notation? Okay. So in Sweedler notation, what are we doing here? Let's do first. Let's start here and go this way. Okay. So what happens? We take the elements of C. I need to make sure that I get the order right. Okay. Let me write it down, and we'll look at, and we'll see which side is which. That'll be our Sweedler practice. So what happens if we go this way? Then we apply F. So we go from little c to F of C, and then we apply the coproduct of F of C, and that is represented by this, right? Take this, the coproduct of F of C, and is denoted by this. And if we take it the other way around, then we're going to get this. So you apply the coproduct, and then you apply F tensor F to that. And so that's what we did over there. Okay? So that's the Sweedler notation for this. Okay? And, Well, for this one, it's just that epsilon, if you start with an element of here, that's going to be the same thing as applying epsilon d of f of c. Okay? And so we write this in formulas, and we write it in diagrams like this. And you can go back and forth depending on what you need. Okay? Is that good? Any questions? Okay, so let us now do some work with this stuff. So maybe before we go into proving some structural things about this, I mean, I hope you're asking yourself, okay, you know, what does it mean to be a subcoalgebra? What does it mean? In algebras, you have ideals, so what does it mean to be an ideal in this context? And we're going to answer those questions. But before we do that, let's practice with a concrete example, just to make sure that we are on the same page. Okay? So let's talk about a concrete coalgebra homomorphism. We'll see what that looks like. And we're going to do it with our two favorite coalgebras so far, which are the coalgebra of posets and the coalgebra of a set. So here's an example of a coalgebra homomorphism. Let's start with a set. Okay? And I'm going to define two coalgebras. So one I already defined. It's just the coalgebra of linear combinations. And remember that in this coalgebra you have that the coproduct of a generator is just it tensor itself, and the counit sends every generator to 1. Okay? But I also want to build a poset coalgebra out of a set. How can I do that? Well, I need a poset, right? I have a set, so how can I make a poset out of a set? There's a couple of things that I could try to do. One would be to just force some order on here, but since we don't know anything about the set, it's a little bit hard to say how you would want to put that order. The other thing you could do, and a very natural thing, is just to consider the collection of subsets of S. And that is very naturally a poset. And so we're going to consider this. These are the subsets ordered by inclusion. Right? And then we're going to define the I'm trying to remember if we gave this incidence coalgebra a name. Do you remember? So we had a poset and we built the incidence coalgebra, but I don't know if we denoted it something. I guess I called it C of P. Okay. And so what is our poset? Our poset looks like this. The bottom element is the empty subset. The top element is the whole set. And then here you have all the different subsets ordered by inclusion. Okay? And remember that our coproduct was this thing where you take an interval and you split it into two subintervals in all possible ways. Okay? So now I want to define a coalgebra homomorphism from C to D. Okay? So do you guys have any ideas how I could do this? I take a generator here, which is just a set element. What should I send that to? I need to send it to something in this coalgebra this coalgebra is linear combinations of intervals, and so presumably I should send that S to some interval here. So can you think of a natural interval to send it to? Yes, no, maybe? Where do we find S over there? S is an individual element, right? And so where are we going to find it in this, which is the poset of all the subsets? We're going to find it right here, actually. So here are the elements of S, right? S1, S2, etc. Okay? So S is going to be one of them. This S, okay? And so I need to choose an interval over there. So which one would you choose? There's some options. I don't know, which one would you choose? The singleton. So just the interval from that point to itself. There's other options that you could try to choose, right? For example, you could choose the interval from the empty set to S, or you could choose the interval from S to the top. I think those are the natural choices, okay? And so maybe you try all three and see which works. So I'm going to take your suggestion, and we're going to try the first one and see if it works. Hopefully it does, and if not, then we'll see what happens. So what is the one that we're talking about here? We're talking about the interval from the singleton S to the singleton S. So I'm only going to do this once. But really, I'm just going to write this as the interval from S to S. And we'll just remember that there's supposed to be brackets everywhere, but I'm going to get tired of writing them everywhere. Okay? So there we go. And so we're taking the, S is some set that we can think of it as being a bunch of elements. And so we're going to take this, any given element here, to the interval from here to here. A boring interval, okay? But it's an interval. So let's see if this actually satisfies what we need it to satisfy. Okay, so what is the coassociativity? The coassociativity says that, so let me put the arrows, and then we'll fill in the blanks. So here is our basis element of C. So we take an individual element, S. Okay? Now, if we take it this way, this is just the map. So this is F, and this is coproduct and coproduct, and this is F tensor F. So when I map it, I map the singleton to the interval from S to S. Right? Okay. Now, what happens when I apply the coproduct to S? Well, I know that that goes to S tensor S. What happens when I apply F tensor F to S tensor S? I'm going to get the tensor of, so F is applied to S, and I get this. And this F is applied to this S, and I get this. And now I need to make sure that this does commute, so this goes to here. So I need to check that delta of S comma S really is equal to this. So let's see if it is. Okay? So what I'm going to do is that I'm going to just take any subset here and compute delta of the interval from T to T. And this is going to include in particular when T is a singleton, but I'm going to compute the coproduct at any T comma T. So what do I get? Remember, what you do is that you look at all the things in between this one and this one in the poset, and you go the bottom interval and then the top interval, the bottom subinterval and the top subinterval, right? How can U be between T and T? U has to be equal to T. And so there's only one term in this sum, and it's going to be when U is equal to T, and I get T, T, tensor, T, T. Okay? And so this actually commutes. This This is coassociative. Okay? All right. And does it send 1 to 1? Or rather, co1 to co1. I'll let you check that, but it does. It's pretty straightforward, so you check it, and it works, okay? And so this is an example of an incidence coalgebra. Oh, sorry, of a homomorphism from a set coalgebra to an incidence coalgebra, okay? Now, one thing that you'll realize is that this map is clearly injective, right? Every generator gets sent to somebody different. All the things are linearly independent. And so this is actually an injection, meaning that we can really think that inside our incidence coalgebra, we have our set coalgebra, right? And so this means that we should really be thinking of this guy as a subcoalgebra of this one, okay? And so that's what we're going to do now, is start saying, okay, what does subcoalgebra mean? All of that stuff. Okay. So let me make a couple of definitions. So let's go back to some definitions from algebras, okay? So if you have a B as a K algebra, and A is a subspace, as a vector space, then when is A subalgebra? Well, A is going to be a subalgebra if it's preserved under multiplication. So we need that M of A tensor A should be inside A. Anything else? You actually have to remember that subalgebras need to contain 1. Right? And so we're going to demand that the 1 of B is inside A. Okay? And that doesn't come for free, actually. You really have to say that. And the other important definition is that A is an ideal if when you multiply things in A by things in B, you get things in A, whether you do it on the left or on the right. Okay? Of course, this is what we call a two-sided ideal. Something that is a left and right ideal. Okay? So we wanna give similar definitions for what it means to be a subcoalgebra. Okay? So if you have D is a K coalgebra and C is a subspace, we're going to say that C is a subcoalgebra if when you apply the coproduct of anything in C, that stays inside C tensor C. Okay? So think about it. C is inside D, and therefore C tensor C is inside D tensor D. And so you want that when you apply the coproduct of elements in C, you don't leave C. So it's the analogous condition. And I'm going to say that C is a coideal if the coproducts of C live inside C tensor D plus D tensor C. And again, this is going to be called a two-sided coideal. Okay? And maybe it's a little bit less obvious why this should be the definition of coideal, but I hope to convince you in the next few minutes why this is really a good definition. Okay, so let's prove a few things. So for example, one natural question is that if I define coalgebras and algebras to be somehow dual to each other, and if I define homomorphisms to be also kind of dual notions, then it's a natural question to ask, well, if you have a homomorphism of coalgebras, can you dualize it and get a homomorphism of algebras? Okay? So we're going to prove that that's the case. So duality of homomorphisms. So here's the proposition. If I have a map of coalgebras, okay, then we talked last time how we mentioned last time how you can take the dual of that map, and that takes duals of everything and reverses the arrow, and this is going to be an algebra map. Okay. Okay. So here I need your help because this is we're going to do a computation and it's going to take concentration and it's going to take making sure that we use Sweedler notation carefully. Okay. So please help me out here while we check this. What do we need to check? Well, we need to check a couple of things. To be an algebra homomorphism, you need to preserve multiplication and unit. Okay, so let's check multiplication. So we need to check that that f star is multiplicative. In other words, if I take two elements of here and I multiply them, I get the same thing as if I do it like this. Okay, where D star and E star are in D star, right? Okay, so how are we going to do this? Well, first of all, where do these things live? So we have D star, E star, which lives here. I mean, first of all, D star and E star are in capital D star, and D star is an algebra because D was a coalgebra. Okay, and therefore, when I multiply them, I can multiply them, and I'll be in D star. So this is in D star, and when I apply F star to it, I'm going to land in C star. So this is an inequality that lives in C star. It's an equality of linear functions on C. And so to check that that equality is true, let me just evaluate at a point in C and see if I get the same answer. So let's compute the evaluation of this thing at some element C, where little c is an element of big C. Okay. Okay. So what do I do? Well, the first usual thing is that when you have the dual map here, remember we can send it over here into its dual form. So we can send this F star over here, and we're going to get F of C. Okay? Now, what is D star, E star? Well, it's the multiplication of D star and E star. Okay? Now, remember, how are we defining M here? M is the multiplication of my algebra D star. That multiplication comes from, it is the dual of the co-multiplication of D. Okay? And so I'm going to write it as delta star is the dual to co-multiplication. Okay? And again, I have a linear map over here in the dual, which I can send over here and get D star tensor E star, comma, delta f of C. Okay? Do we agree so far? Okay. So let's see, what can I do now? The left-hand side is not, it's not clear that I can do anything to it. Can I say something about delta f? Delta f c. So let's see. I like to look at it in the picture. So let's look for it in the picture over here. So let's look for delta f over here. So in this picture, I start with an element of c, and then I apply, here's delta f. Delta of f of c lives here in D tensor D, which I think is what you were saying. But now as I look at it here, I know what I should do, right? Because if what I'm doing is this, it seems the natural thing to do is just to say that I'm going to go this way. And I can do that because I have a coalgebra homomorphism, which is great because that's what we want to use. So let me write, instead of delta f, I'm going to write f tensor f of delta. Okay? So this is equal to D star tensor E star, comma, and then delta f becomes f tensor f of delta of C. Okay. And now let me switch to Sweedler notation. Because I have my coproduct and I'm applying a bilinear function to it in front. So I can write this in Sweedler notation as summation over the elements of C of this thing evaluated at C1 tensor C2. So what I get is f of C1 tensor f of C2. Okay? And so then I'm going to say this bilinear form is bilinear, and so therefore I'm going to take out the summation. So sum over C. And now when I pair up this with this, what I'm going to do is that I'm going to take D star at this guy, and I'm going to multiply it by E star at this guy. And so what I get is D star evaluated at f of C1. I forgot the parentheses here, right? It's a Sweedler notation. So at f of C1 times E star at f of C2. Okay? And okay, so let me leave it like that for now. So this is in Sweedler notation, this is what I get when I use the left-hand side. Okay? Let's do the right-hand side now. So what happens when I evaluate f star of D star, f star of E star at C? So again, well, I'm going to do it a little bit faster now because I'm kind of repeating the computation. So here I'm multiplying these guys. Now you should notice that this multiplication is different from this one, right? Because here I multiplied elements of D star. And here I'm multiplying elements of C star. So if I was really very careful, I would put M sub D star here and M sub C star here. But it would look really ugly. So I'm just doing it like this. Okay? Again, M is delta star. And so let me take delta over here. And I get delta of C. Okay? But let me just take delta of C and write it in Sweedler notation. So in Sweedler notation, this is going to be summation over C of C1 tensor C2. Okay? And then, again, this is linear. This is bilinear, so I can do this and make this guy apply over here. And I get F star D star comma C of 1 times F star E star evaluated at C of 2. Okay, and hopefully I haven't made any mistakes and I can see why these things are equal to each other. So are they equal to each other? Well, if we look at this thing and this thing, we're going to see that they are the same as soon as I take this F star and send it over here. I'm going to get that. And then if I take this guy and I do the same thing, I'm going to get this one. Okay? And so that's the proof that these are actually equal to each other. That's great, no mistakes, and it worked out. Okay, so F star is multiplicative. And then you also need to check the unit, but that's a lot easier. Okay. But that proves this proposition. Okay. So these are the kind of computations sometimes you're stuck with them because this is just how coalgebras work. Okay. And if you try to do it without Sweedler notation, it's just you're gonna do the same argument and it's gonna look longer. Okay. But the good news is that once you've proved this, you never have to do this again. Okay, so now we know this, and we kind of expected it given this setup. Okay, but there's a proof that this actually works out. Naturally, there's a dual statement. So what is the dual statement? The dual statement is that if well, I'll write it over here. Dually, if I have a map of algebras then the dual is a map of coalgebras. Do you guys agree with this? Is there any reason for concern here? Is it obvious? One thing you should remember is that the way that duality works is that any coalgebra has a dual algebra, but that's not reversible. If you want to start from an algebra, our construction of the dual demanded it to be finite dimensional. And so let's put here finite dimensional. Okay. And then that's true, and the proof is basically the same. Okay, very similar. By the way, I put in the forum the question of what happens if things are not finite dimensional. So you should go there and think about it, and we'll talk about it in the forum. Okay? All right. So that's it. duality is really nice with respect to homomorphisms. Okay? So the next thing that we're going to check is that we define these notions of subalgebra, ideal, subcoalgebra, and coideal. And what I'm going to show is that also there's a very nice duality there that is less obvious. Okay? So I'm just going to erase all this stuff so that we can keep the definitions and we can keep the homomorphisms. Okay? But actually, I'm realizing that before we are able to explain that duality well, we need to review a little bit of linear algebra. And what's the reason for that? The reason is that, for example, if we want to dualize the situation and we want to understand what is the dual to subcoalgebra, then we're going to need to take the dual not only of we're going to need to take the dual of C and D. And so the question is, how do you take the dual of a subspace of a space? Okay? And so that will bring us to a little bit of a review of linear algebra. So let me do that over here. I think it's going to fit. Okay. So let's take a vector space. So what we're going to do is review dual subspaces. Okay. And by the way, I'm sure you've seen this before, but maybe not in this language, but in the language of orthogonal subspaces. But it's kind of the same thing. So what I'm going to do is this. I'm going to take a vector space V, vector space, and V star is going to be the dual vector space. Okay. So given a subspace S of V, what do we define the dual subspace to be? So we need to define something which is a subset of V star associated to S. And the natural thing to do here is to do what is called S perp, which you might know as the orthogonal complement, but the thing to realize now is that the orthogonal complement really lives in the dual space from this point of view. Okay? So we just define this to be the things in V star. Okay, what should these things satisfy? So these are functions on V. What we're going to do is we're going to demand that they make S vanish. So V of S should be equal to 0. Okay. Sorry, V star of S should be equal to 0, and I'm going to write it like this. So V star evaluated at any element of S should give you 0. Okay. That's the dual subspace. Similarly, if you have something in V star, then T perp lives in V, and it's going to be the vectors in V that are annihilated by this thing. So any linear function in T kills this element and sends it to 0. Okay? Dual subspaces. And one thing to recall is that if you apply this operation twice, you're going to get back what you started with. Okay? So these are the dual subspaces. Okay? And so now what I would like to know is what happens if I So here I had C subset of D is a subcoalgebra. What I want to know is what happens if I take a subcoalgebra and I take its dual. And if I'm lucky, then it's going to be something nice. Okay? And actually, I'm very lucky. I mean, I guess it's not luck, right? It's just the setup is nice enough for everything to work nicely like this. So if C is a coalgebra and C star is the dual algebra, and D is a subspace of my coalgebra, then D is going to be a subcoalgebra if and only if what's your most optimistic guess here? There's not that many guesses, right? I mean, we've talked about two notions here. If everything works out, it'll be either a subalgebra or an ideal. Let's take a vote, okay? So you have to decide if you think this is a subalgebra or an ideal. Okay, so who thinks you get a subalgebra? And who thinks you get an ideal? And why did I get so few votes? Let's try this again. I want everybody to vote. You have to decide even if you have no information. So subalgebra. Now you're changing your vote? Subalgebra, ideal, and two indecisives. Okay. Neither? You're not an optimist. It's an ideal. So I think this is pretty cool and pretty unexpected because when you live in algebras, you talk about algebras and ideals, and then when you go to the dual, you see that there's actually some kind of duality between those two concepts. Okay, so let's prove this. So let's go first in this direction. Okay, so let's suppose that D is a subalgebra of C. Okay, so what can I say? I have an inclusion from D to C. Let's call it I. And so that I'm going to get a dual map, right? This gives me an algebra map, an algebra homomorphism. By the way, have I been clear enough that when I say map, homomorphism, morphism, I mean the same thing? So map is the shortest, so that's the one that I say the most. So I get a dual algebra map from C star to D star, okay? Now, I want to prove that D perp is an ideal. How do you prove that something is an ideal? Well, there's the most obvious way is by the definition, right? Multiply it by something. Take an element of your supposed ideal, multiply by something, and make sure you land in the ideal. There's another slick way of proving that something is an ideal, which is to show that it's the kernel of something. Yeah? Because kernels are always ideals. And so what I'm going to claim is that actually, by the way, so I could do the first thing, that also works. But I'm going to do something a little bit shorter. I'm going to prove that D perp is the kernel of this map. And if it's a kernel, then it's going to be an ideal. And this is actually pretty easy because what does it mean to be in the kernel? And again, let me use the right symbol. So because this goes from C star to somewhere, let me call an element little c star. What does it mean to be in the kernel of I star? Well, that means that I star of C is equal to, wait, C star is in the kernel of I star if I star of C star is equal to 0 in D star. That means that if I take I star of C star and I evaluate it at anything in D, I get 0. Right? I'm realizing that I wrote this wrong on my notes. So how do we conclude here? Dualize, and I get that C star, comma, I of D is 0. But this is just an inclusion. I of D is D. And so this is equivalent to saying that C star is perpendicular to D. It's orthogonal to D. So this works out nicely. Okay. So this is kind of the easy part, and the other part is actually a little bit trickier. And again, I'm gonna ask for your help because this is a little bit of an intricate algebraic argument. So let me ask for your help, and let me also ask you to stop me if there's anything I say that you don't believe. Okay, just make sure this is right. So let's take an ideal. D perp be an ideal of C star. I'm going to have to be a little bit more intelligent now about this. Now, what do I need to show? I need to show that D is a subcoalgebra. In other words, what I need to do is that I need to take an element of D and take the coproduct and make sure that it lands in D times D. So let's take an element of D, and I need to show that when I take its coproduct, it lands in D tensor D. Okay. I know that it lands in C tensor C, okay, because we're in the coalgebra C, but I want it to be in the smaller space D tensor D. Okay, so let me take, okay, so let's write delta of D as something that lives in here, okay? So I'm going to write it as xi tensor yi, okay? And I'm not going to use Sweedler notation here because I really want to look at individual things here. So let me make one comment here. Actually, I used y and z here. I'm going to get confused if I don't do the same thing. So y, z. Where yi and zi live in D. Okay. So now let me make a comment. Note, I can assume that zi is a linearly independent set. Why is that? I mean, what I'm claiming is that if the zi's are not linearly independent, then I can rewrite this expression to make them linearly independent. Why is that? Because if zi is some linear combination of other ones, let's say like this. Sorry, this is the lowercase I over some values of j. Then I can take this tensor yi tensor zi and write it like this, sum over j lambda j yi tensor zj. And I can take this thing and merge it into the term yj tensor zj. Okay? And therefore, I dropped the variable zi, I just made it be absorbed by the other ones. Okay? So that's why I can assume that the zi's are linearly independent. And we'll see in a second why we want to do this. So, claim, I'm going to claim that every one of these guys lives in D. Okay. For all j. Okay. Which is good news because we're trying to prove that this thing lives in D tensor D. And it helps if I put the left coordinate, all of it in D. Okay.
And those yi and zi, you say that they are on D, but they are on C, right?
I'm sorry, say that again?
The I, Z, I están en C, no en D.
Ah, sí. Yeah, thank you. I'm taking the coproduct of an arbitrary element, and I'm trying to prove that it lands in D tensor D, but I don't know that. So these guys, what I know is that they're in C. Thank you. Okay. So let's prove this claim. So to do it, I'm going to assume that that's not true. Assume that yj is not in D. Okay. Now, what am I going to do? Remember that we're trying to take properties of relate properties of D and properties of D perp. So how do I say in terms of D perp that yj is not in D? If yj is not in D, that means that I can find something in D perp that is not perpendicular to it. So I can find something in here such that when I pair yj and D star, I don't get 0. Okay. Because if I could not find such a D star, then yj would be perpendicular to everything in D star, and I would get this. Okay. Okay, so I have this. Now, also, I can do this. The zi's are linearly independent in C. Okay? And therefore, I can find let me say it in two ways. The zi's are linearly independent, and so they're part of a basis. Okay? Now, given any basis of a vector space, we have the dual basis, which an element of the dual basis takes one of the zi's and sends it to 1, and everything else goes to 0. So let me take that guy. So let me take this element such that when I pair it with zj, I get 1, and when I pair it with every other guy in this set, I get 0. Okay? So here what I'm saying is if you have a bunch of linearly independent vectors, then I can find a function that is 1 on one of the vectors and 0 on the other ones. Okay? So I take that function. Now, I have D perp, which is an ideal of C star. I have something else in C star. And if you're in the ideal, then when I multiply these two things, I need to land in the ideal. Right? That's what it means to be an ideal. since D perp is an ideal, I get this. Okay? And then I'm going to say the following. I have an element of D perp, and I have an element of D. So when I make this guy operate on that guy, I should get 0. Okay? So I get that 0 is equal to D, comma, D star, Z star. Okay? Okay, so what am I going to do now? Again, let's remember that this multiplication this is the multiplication like this. And again, it's good to go back and forth from the one to the dual. So M is the dual of delta. And I can send delta to the other side. Okay? I know what delta of D is. I called it summation of yi tensor zi D star tensor Z star. I use linearity, so I get the summation on I, and now I get, remember that the way a tensor acts on this is this with this times this with this. So I get yi paired with D star times zi paired with Z star. Okay? And then I say, well, I know what this is because this is 0 almost always. The only one that is not 0 is this one. Okay? So this is going to be 0 for every I except for the case j. So I get y j D star times 1. But also, you see that I prepared this ahead of time because now I also built everything so that here this is not 0. And that's a contradiction because I started with 0 and I ended with not 0. It's a contradiction. Okay? So that means that the yi's actually do live in D. And notice that it's very important in this argument that the zi's are linearly independent. Because if the zi's were not linearly independent, I couldn't have done this step. And so, but now what do we have? Well, what we have, in conclusion, is that delta of D is in, it's a bunch of tensors, it's a sum of tensors where the left thing is in D and the right one is in C. So I get D tensor C. Okay? And now forget linear independence. This is just a fact about the coproduct, and it makes no reference to the basis or anything like that. Now, naturally, there was no reason to expect that the left-hand side should be more special than the right-hand side. So similarly, delta of D is in C tensor D. Okay? And now let me give you an exercise in linear algebra. Prove that D tensor C. Let me put it in a different color so that you see it and you do it. Because it's a good exercise. So exercise, when I take D tensor C and I intersect it with C tensor D, I get exactly D tensor D. Where we said that D was a subspace of C. Okay? So general fact, and given that delta of D is in both of these, that means that delta of D is going to be in D tensor D. Okay? And so that's it. So you see this takes a little bit more. Here we actually had to do something more than just push symbols around. And there's our proof. Now, I guess you can anticipate also that if subcoalgebras are dual to ideals, then subalgebras are dual to coideals. Okay? And you might have asked yourselves why I made that strange definition of coideal. And one of the several reasons is that it is the definition that makes coideals dual to subalgebras. Okay? And so this is how all of these things are related to each other. Okay? I think this is a good place to stop. Okay? So we'll continue next time.